In our last video, we began to explore exponents and logarithms in more detail, and we took a look at more explicit examples. And we, at the end of the video, began to look at how we might create a table of logarithms, because long before we had these things, long before we had spreadsheets and calculators, we had just our heads and pieces of paper, pencils, erasers, and we had to create these tables on our own. How else would we be able to calculate, a logarithm without a computer? I mean, gee, it would be pretty hard. I mean, computers really simplify mathematics for us. But that's why it's important for us to know where these things came from, how they came about, because that's the only way we're really going to understand them fully. And I may have been a little bit confusing yesterday. I mean, I've done this, and it's been literally 30 years since I went about creating a table of logarithms, just for the fun of it. But last night I sat down and I worked out a few, and I just wanted to give you an idea so that you could see how these things were done. And that, yes, they indeed were tedious. Yes, indeed, people took the time to do it. And they had to have people who were careful, who had good heads on their shoulders for numbers, and they couldn't be as cavalier about calculating as we can be today, because in those days they didn't have a very quick means to recheck themselves. So now, like I said, at the end of the video, we began to explore. I think I probably shouldn't have used log base 5 or any other higher log base, because it leads to too big a spread. And back in the 1600s, when people were creating these tables for engineering, mathematical, science problems, they basically calculated them for base 2, base 2, oops, base 2, base 10, and the natural base, E, which is 2 point, I think, I have to look it up, 2.717, I think it's 2.717, blah, 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 forever. I better look it up because it's been a while. Just want to make sure I'm not lying to you. Here we go. The natural log. Yeah, 2.7, actually 2.718. So that's 2.718. 2818, it just goes on. 2718, 282818, 28 4 590, blah 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 blah. Goes on forever. It's a non-repeating, never-ending decimal. It's one of those. It's like pi. It's like the Fibonacci. It's like the golden number, the golden ratio, and just goes on forever. So the natural base E represented that number. So e to the 1 is equal to 2.7182818, blah, blah, blah. So here we have it. And what they did was if they had other bases, they would convert to base 2 and then get their logarithm and then convert base back to base, whatever base they were in. So they didn't have to calculate tables for every base. They use selective bases. And they use these bases for science. Now 10 has the advantage of, 10 to the 0, 10, 1, 10 squared, and everything. Base 10 is very practical. That's why the metric system works so well. And that's 1, 10, 100, 1,000, 10,000, 100,000, and 1,000,000. And but again, you see how these get very big very fast. And so there was a lot of calculating done to make tables for base 10. So let's take a look at creating a table. Let's say you were on a desert island. You were Tom Hanks stuck in Castaway and you needed to calculate logarithms. Well, we do know that 2 to the 0, 2 to the 1, 2 squared, 2 to the third, and so on. We don't have a tremendous spread. We have 1, 2, 4, 8, next one 16, 32, and so on. So they do go up, and they go up fast, but for the early ones, we don't see that that there's much of a spread. Here there's 1, here there's 2, here there's a gap of 4, 2, and 1. So how do we go about doing that? I don't think I was particularly clear, but first off, we have to. So let's take a look at the interval between 2 to the 0 is 1 and 2 to the 1 equals 2. Okay, and how best can we do that? Well, if we start with 2 to the half times 2 to the 1/2, that equals 2 to the 1/2 plus 1/2 equals 2 to the 1 equals 2. So 2 to the 1/2 is a good starting point. So that's right in between 2 to the 0 and 2 to the 1 equals 2 and 1. So we have 2 to the 1/2 and 2 to the 1/2 times 2 to the 1/2 equals 2. So we're looking for 2 to the 1/2 equals n, where n times n equals 2. And so what is that number n? Well, it's the square root of 2. So we look for the square root of 2. Let's start with 1.4. And this is how they did it in those days. 16, 4, 5, 4, 1, 1.96. Well, that's less than 2. So it's not quite what we want. We could get closer. So let's try 1.1, 1.4, 1.4, 1.41. You can see how we build on it. We got 1.8891, 1.988. It's still too small. So we go 1.414, 1.4. I know these numbers, so back then they would have had to do a little more guessing, but they did pretty good job guessing. So that's 16, 5, 16, 5, 4, 1, 4, 1, 6, 5, 6, 5, and 4, 1, 4, 1. And we've got 6, 9, 13, 10, 18, 19, 19, and this is 10, 2. So did I do that right? I think I made a mistake. 1.414. Yes, I did. This is 9. I shouldn't have carried the number there. So we got 6, 9, 12, 13. That's a 1. 9, 18, 19. This is 9. What am I doing wrong here? I must have done this calculation wrong. Okay, 16. 16. This bothers me. 4, 5. 16, 4, 5. That's 4, 1, 4, 1. And that's 16, 4, 5. 16, 5. And we got 1, 4, 1, 4. We got 6, 9, 12, 13, 10, 18, 19. This is 9, 9, 1. 1.99939. So this is 0.9994. When we round it, that's getting pretty close. And in fact, I think what we end up with is 1.4143. That's 1.4143. Yeah, that's pretty darn close. So this is pretty close to 4. Darn it. 1.414, let's say 2. Okay, let's see what, just make sure. 1, 2, 1, 4, 2. Yeah, that's pretty close. That's our best approximation right now. Okay, so, but what else can we do? We can go in between these two. And if we go to 2 1/4 times 2 1/4 equals 2 1/2. Well, we have that number, 1.4142. So 2 to the quarter is n, where n squared equals 1.4142, and n equals the square root of 1.4142. So that's how we progress. That's how we progress with this. And so we're looking for a number. And so let's say 1.2, 1.2. That's 4, 2, 2, 1. That's 1.44. Well, that's too big. So 1.2 isn't our number. So let's go 1.19, 1.19. That's 81. 81, that's 17, 10. And we got 9, 1, 1, 9, 1, 1. That's 1, 16, 10, 11, 4, 1 point. Well, we're getting closer. It's still too big. So let's bring it down a notch. 1.18, 1.18. Let's say, well, 5, 5. And this is how they went. They narrowed in on it. 42, 9, 5, 40, 68, 8, 14, 9, and 5, 8, 1, 1, 5, 8, 1, 1, 5, 2, 17, 22, 22, that's 10, 24, 10, 20, that's 4, 1.404. So that's too big. So we got to make it smaller. And what we really are looking for, again, is the square root of this number. So so 2 to the quarter equals n equals 1.1892. And so we have 2 1/4 equals approximately 1.1892. And we can still refine it. We can go 2 to the 8th times 2 to the 8th equals 2 to the 2/8 equals 2 to the quarter. And we have a number for that, equals 1.1892. So we're looking for that number, 1 to the 8th, 2 to the 8th equals n, where n squared equals 1.1892, and n equals the square root of 1.1892. And we can guess that that number is 1.09, 1.09, that's 81, 9000, 901, and we got 1, 8, 18, 1.188, 1.89. So we're getting there. And it turns out, for time's sake, that it's n equals 1.09051. So we have 2 to the 8th, 2 to the 8th equals 1.09051. Okay, so now let's look between here and there. What number would be there? Well, 2 to the 0.75. So that's 2 to the 3/4. So how do we get there? 2 to the 3/4. So that's 12/16. So 2 to the 6/16 times 2 to the 6/16 equals 2 to the 12/16. And that's divided by 4 equals 3/4. Okay, so let's write this down a little bit further. 2 to the, well, equals 1.4142. Let's make some room in here. 2 to the 3/4 equals, and this is 2 to the 1/2 equals, so 2 to the 6/16 times 2 to the 6/16 equals 2 to the 12/16 equals 2 to the 3/4, or 0.75. So this is equal to 2 to the 2/4 times 2 to the 1/4. Well, this is just 2 to the 1/2. 2 to the 1/2 times 2 to the 1/4. So we have 1.4142 times 1.1892. See, now we can begin using some of our knowledge instead of guesswork. And then we can, and given how precisely we've multiplied that, the error that we introduce is going to be small. So 1.4142 times 1.1892 equals 1.6, 1.68177. So 2 to the 3/4 is equal to 2.5 times 2 to the 1/4. And let's see, how close we came. So 2 raised to 0.75 is 1.618. We got 1.68179. So 1, 2, 3, 4 decimal places were about right. We're a little off, but not much. And then here we could go. What can we do here? Well, we could say what's 2 well, that's actually higher. So we should have put 3/4 here. Sorry about that. 1.68179. And we leave this. I'm sorry, I shouldn't have put that there. So we have these numbers. We have 2 to the 0. Let's write this a little bit more neatly. We have 2 to the 0 is 1. 2 to the 1/2 equals 1.4142. 2 to the 3/4 is equal to 1.68179. And 2 to the 1 equals 2. So now we just go log. So log of 2 to the 0 is 0. Log base 2 of 2 to the 0 equals 0. And so on. It's always just the exponent. So we have n, the exponent on this side. So we got 0, 1/8, 1/4, 1/2, 3/4, and 1. And that's equal to the log base 2 of 1.09051, 1.1892, 1.4142, 1.68179, and 2. So here we've created a table between 2 to the 0 and 2 to the 1. And we can build on that. I mean, 2 to 1 and 1/4. Well, that's 4/4. That's 5/4. 5/4. 16ths. Let's see. That's 20 16ths. And that's equal to 2 to the 10 16ths times 2 to the 10 16ths. Okay, so 2 to the 10/16 times 2 to the 10/16 equals 2 to the 20/16. And 2 to the 20/16 is equal, well, if we divide by 4, is equal to 2 to the 5/4, and that's equal to 2 to the 4/4 times 2 to the 1/4. And we have that number. 4/4 is just 2 times, and the 1/4 was 1.18, so it is 1.1892. And so we have 5/4. 5/4 is, whoops, I got this backwards. 4 into 5 is 1, 1, 0, 2, 8, 2, 0, 5. So we have 1.25 equals log base 2 of 2 times 1.18. So let's do that multiplication. 1.1892 times 2 equals 2.3. 2.3784, and that's what this logarithm is, 2.3784, and so on. So now you can see how we can build our table of logarithms, going on and on and on. And this is all base 2. And remember that this side are the exponents. And we could always just, see, 8 into 10, 1, 8, 2. That's 2, 16, 4, 0, 1.25, 0.125. So that's 0.125. This is 0.250. This is 0.500. This is 0.750. And this is 1.00. And this is 1.25. 1.25 equals. And so we can go to decimal form, and that's how you normally see logs, tables of logs. And if you need a number in between here, you interpolate. The interpolation is going to be off a little bit, but not too bad. But this is how tables of logarithms were made. And people just sat there doing these calculations. They went to smaller and smaller divisions. You could go to 2 to the 16th. You could go 2 to the 32nd. You could go 2 to the 64th. And they went to these fine degrees. I mean, we just did small or large intervals, relatively large intervals, 0.125 to 0.25 and so on. So you could refine that and really bring it down to a very narrow degree of inaccuracy. So that's what people did for a long time, and they kind of students were put to task creating these logs, tables of logs in the 1600s. But that's how it was done, and I think it's pretty cool. And you understand how it's made 0.000000. Okay, so that's how these things were created. And I think once you understand how they're created, you have a better understanding of what they mean. What does it mean to take the log of a number? Well, it's the power. It really is the power to which a base is raised. And so earlier I had introduced a couple of ideas. I said base 10, base 2, and the natural base. So two bases, bases 2, 10, and E, which is 2.718, blah, 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 were the bases that were commonly used. And this one is because it came up, they call it the natural exponent because that number 2.718 came up in natural problems all the time. So that was a base that was important for scientists to work with. Okay, so now let's move on to another aspect of this. Now we're going to take a look at the laws of logarithms, and I think this is pretty cool. This is pretty neat stuff. So what if we had the situation where we have a times b equals n? Well, if we took the logarithm base n of a times b, we have the logarithm base n of n. But what if, as we know, we can put b in terms some power to equal a? So then we have log to the a times a, or I'm sorry, is a to the some power. B is equal to a to some power. So we have a to the power equals log, but n is a times b. So this is by the law of exponents of a to the p plus 1 equals log n of a times b. And then we do our, oh boy, I'm going too fast, our rule of logarithms, p to the p plus 1 times log n of a equals log of n sub n times a times b. So we have p times log sub n a plus log n of a equals log of n of a times b. But we know that that's the power of a, so we got log n of a to the p plus log base n to the a equals log base n of a times b. But a to the p is b. So we have log n b plus log n a equals log n of a times b. So now we've just proven a very important rule in logarithms. So the log of a times b is equal to the log of b plus the log of a. So that's a very important rule. And by extension, we can say this, that this is, we could use a divided by b equals n. And so if we went log of a divided by b equals log of n, and we can say that a to the minus x equals b, 1 over b. So we have log n of a times a to the minus x equals log n of a divided by b. And then we have the law of exponents. We got log base n times a to the 1 minus x equals log base n of a divided by b. Then we take this out, 1 minus x times log base n of a equals log n of a divided by b. And then we just take that out. We have log n of a minus x log of a equals log n of a divided by b. And we got log n times a equals, minus log n of a to the x equals log n a slash b. But remember, a to the minus x equals 1 over b. So a to the minus x raised to the minus 1 is a to the x is equal to 1 on b, or b to the minus 1 raised to the minus 1 equals b. So a to the x equals b. So we use that to derive our other rule. We have log base n of a minus log n of that a to the x is b is equal to log n of a divided by b. And that's our second logarithm rule. And that's a very important rule that we're going to be using. So really, a division is a special form of multiplication when you stop and you think about it. So this is only natural. So we have shown two important rules for logarithms, or laws. I don't know what you call them, rules, laws, whatever. A law is a mathematical rule, sort of like Newton's law. Newton's law is basically a mathematical rule that the force between two objects is equal to the gravitational constant times the mass of the first object times the mass of the second object over the distance squared between the two objects. So if you have object mass 1 and mass 2, and we have r, that's the gravitational law that governs the force interaction between these two objects. And we call that a law, Newton's law, but it's basically an empirical mathematical formula. So I'm not sure that rules or laws are really very different. People kind of have the idea of law as being an ultimate. We did find that Newton's law was erroneous when Einstein showed through relativity that gravitation could be described as the warpage of time and space. But Newton's law gives the wrong impression that that is an indelible thing that can't be changed. So let's see, are there any other interesting things that we can look at? Well, at this point, I think maybe we should call it quits. Why don't we just run through some of the laws, rules of exponents that we've considered up to date. And this is basically a summary. So x to the n equals x times x times x dot 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 times x n times. So if n is 3, x, and terrible, aren't I? Oh, if n equals 3, x to the 3 equals x times x times x. So that's basically all that's saying. That's an important rule. Then we have x to the a times x to the b is equal to the x times a plus b. That's very important. But the important thing here is, one, that it's the same base, x, and two, it's a multiplication. So that rule has these two contingencies. And notice everything is really dealing with multiplication. Then we had that x to the a raised to the b is equal to x to the a times b. And then we had logarithms, log base n of x to the n is equal to, well, let's say p, x to the p. We have p log base n of x. So we got 1, 2, 3, 4, and now number 5 is log of a times b is equal to log n of a plus log base n of b. And finally, our last rule, number 6, that we've considered so far is the log base n of a divided by b, and that's equal to log base n a minus log base n b. And so that kind of wraps it up right now for the rules for exponents and logarithms, and we'll be looking a little more deeply into this, and especially the applications. So until next time, I wish you all well.